This podcast is brought to you by the School of Advanced Study, University of London. All of our podcasts are available from our website, www.sas.ac.uk.
Well, thank you, Colin. I'm really glad to be here for a whole lot of reasons. It's been a great day seeing a lot of people, some of whom I knew and some people who I never knew. So thanks to all of you for coming, and I hope I can amuse you for the next 45 minutes or so. So I'm going to talk about vision, obviously, and I'm going to talk about what we see, and I'm going to present some ideas in what I hope is a provocative way, because I want you to, whether you like what I'm saying or not, or believe it, I want you at least to think about it. I think these ideas are worth thinking about, maybe even critical to think about if you're interested in vision. So let me begin by, maybe we could turn the lights down a little. Do these probably are sort of all or nothing lights? Oh, perfect. Okay, right there. Good. Okay, so I always like, when I hear a seminar, to know what is this person who's talking to me interested in? What's the motivation for doing this? What's this work about? So let me begin by telling you that. This is the cover of a book by David Hubel and Torsten Wiesel that actually was published by OUP fairly recently in 2006. And it's a book that summarizes their 25-year collaboration, as the title suggests here. And for those of us who grew up in neuroscience in the 70s and 80s, these were the iconic figures who really, in North America at least, were the major drivers of thinking about the senses, of thinking about the pathway from the periphery to the cortex, and for establishing what all of us in that era imagined would be a quick explanation, or a quick route to the explanation of how it is that the anatomy and physiology of the visual system in cats, in monkeys, and by implication in human beings, how it leads to a visual perception. Visual perception being, by definition, what we actually see, and really, in a sense, the end stage of processing by the visual system. And that intuition that the answer would soon loom into sight, and that vision would be understood, never really came to fruition. And by the 90s, these guys, as you probably know, won a Nobel Prize in 1981 for this work, and was rightly recognized as absolutely fundamental to thinking not just in vision, but in a whole lot of aspects of brain function. What became apparent by the late 80s, early 1990s, and the beginning of this century is that it really wasn't working out, that after 50 years, people really still didn't understand perception. They didn't understand how it is that the nuts and bolts of vision, in terms of cellular connections and mechanisms, leads to the perception of all the things that we're aware of when we look around the world. And this is an outline of what I'm going to tell you, and let me run through it. And what I'm going to start with is convincing you, and I don't think this is the easy part of the talk, convincing you that what we see is not really the physical world, and that the phenomenology that I'm going to show you in a second is a very good place in starting to think about the history of vision science in the last 50 years, and why it is that the program that seemed to so certainly to complete the story of vision under the guidance of Human Weasel. There are many acolytes and all the people involved in research over this period, why it's not come to a happy conclusion. So the second point that I'm going to make, and it's really the critical one here, and all of these are provocative, as I said, ideas that you may like, you may not like, but I hope you'll at least have an open mind about their merits. Second point is that the challenge for human vision or any visual system over the course of geological time is that light stimuli are really unable to convey information about the real world. That seems highly counterintuitive. We look around, we see colors, we see forms, we see intervals, and we behave obviously with routine success. So how could it be that we're not seeing reality? How is it that our visual systems are not doing for us what the instruments of physics do for the physicists? That is, actually measure the reality of the world. That's the second point. The third point is that this is the problem, and that visual animals circumvent it by creating and restricting stimuli that goes to those that produce reproductive success. So I think there is a solution that evolution has hit upon for this problem, and again, you may or may not agree with what I'm going to suggest is that pathway to understanding vision in a more complete way. Fourth point is that the frequency of occurrence of stimuli, again, quite counterintuitively, actually predict what we see. They explain the phenomenology that I'm going to show you momentarily. Fifth point is that when you take all this into account, it really seems that vision and visual perception is not fundamentally different than any other reflex response that a sensory motor system makes. Again, that may strike you as an odd thing to argue for. And finally, I'm going to try to make the case that the best way to understand the purpose of the nuts and bolts of the visual system, ours and other experimental animals, is by actually trying to evolve the visual system. Again, how could you possibly evolve a visual system? Well, I'm going to give you some ideas about that. So let me begin by the first point, which is that we don't see the physical world, and that this is a pretty good place to start thinking about what's the problem. If we don't see the physical world for what it is, what does that mean? And how does it tell us about a possible pathway to thinking through what vision is actually about? So I'm going to show you just a few examples. There are many. We could spend the whole hour looking at interesting phenomenology of vision in color, in form, in motion. I'm just going to show you a few examples to get you thinking, and I hope convinced, that we're not seeing the world that we look at all the time, 24 hours, well, not 24, 12 hours a day when we're awake. We don't see the physical reality that's actually out there. And to do this, I'm just going to, the examples I've chosen are all from the perception of luminance. Luminance is a physical measure. It's a measure of the intensity of the light that falls on the retina. The perception that comes from that is called lightness. Lightness is, the impression we have of the lightness or darkness of a surface, and that's coming from the luminance that visual stimuli generate. So probably most of you have seen something like this. This is in all the textbooks of Psychology 101. These are two gray patches that are physically identical. That is, if you take a photometer, ordinary instrument in all your digital cameras these days, that measures the intensity of light coming from these two patches, they're physically identical. But if you put a surround on these two patches. Nothing has changed here. These are still the same two patches. You immediately see the one in the dark surround as being lighter than the one in the less dark surround. And so people have known this for probably forever.
I'm really sorry about this, but I can't take any requests at the moment.
I haven't mastered my iPad yet, so you can understand.
So this is an effect that's well known, and it's been presented in all the textbooks as an illusion, a simple example of a visual illusion. And this is...
One clarification.
Yes.
As you put the two dots, I, right from the beginning, saw the dot on the right as being more darker than the one which I've circled now.
I did slightly as
Oh.
well. Slightly.
Well, there should be. Maybe it's Colin's projector. Maybe he's got a cheap projector, but none of these...
It's only a philosophy department,
None of these, there's no trickery in this. And I'm going to show you at the end my website, and you can go and look at all these things on the website and, test to your own satisfaction that these are all real phenomena, that there's no hocus pocus involved. So this difference, of course, you see immediately. This is not like adaptation when you go into a movie theater, come out of a movie theater. This happens as quickly as you could put on, or I can put on or take away the surround. So this is kind of one indication that we're not seeing the reality of luminance, the physical measurement of light intensity, for what it really is measured with a physical instrument like a photometer. Not a very impressive effect, so let me show you an effect that is more impressive. And this is a picture, and I want you to consider the apparent lightness of this region, and this region, this region, and this region. I think you will see this, all of us see this as this being much lighter than this being much lighter than this. But again, if we mask out the information that's coming from the context here, these again are exactly the same luminance values, and they are immediately appearing to you as something approaching quite a light gray here and a dark gray here, when in reality these are coming from exactly the same luminant patches. So that's just, and again, this is not a new finding. People have known this since at least the 1920s, that basically you can take a piece of paper that's white and make it look either white or something very close to black by the context that you put it in. Again, a very compelling demonstration that you're not seeing the world for what it is physically. And this is another example, and the last one I'm going to show you in this little trilogy, that indicates there's no really simple explanation of this. So you might think, well, gosh, in the first one, anytime you see a patch that's surrounded by dark and a patch that's surrounded by light, that's all this is about. This is something called the corn-sweet effect, described, 35 years or so ago by the psychologist Tom Cornsweet. And here, this patch, this surface region looks quite different, darker than this. And in this case, what's interesting and puzzling, you can forget all the folderol and the surrounding, that's just decorative art. What's interesting here is that the difference now is coming just from this little edge here. That's an opposed gradient going from gray to black and from gray to white. And you can do this by masking it out with your finger, but I'll mask it out here for you. As soon as you mask out that edge, called the corn-sweet edge, you do away with the apparent difference between the two surfaces. Again, happening as quickly as I can put on or take off the mask. So the question here is, what's going on. And again, as I said, I mean, I could show you similar demonstrations, and you're welcome to look at them to your heart's content on my website or Volato's website, who made a lot of these effects as well, or other websites that are out there showing you that whether it's color, whether it's form, whether it's motion, whether it's light or dark, we just don't see the world for what it is physically. And the question is why? And one point I think that's important to remember as I go through all this is that what textbooks call visual illusions really aren't illusions. This is just the way we're seeing the world all the time. I mean, you can kind of make these, as I showed you in the first two examples, you can make a fairly weak effect stronger. But this is just the way we're seeing things all the time. These are not anomalies that are trickery, from laboratory hocus pocus. This is the way we're seeing the world. As I say, it applies to all the basic qualities of vision. So this is a big problem. And the second point I want to dwell on here is that the major challenge for the evolution of vision, whether it's us or any other visual system, is to somehow figure out a way to perceive stimuli in a manner that's coming from a world that really can't provide any information about what's out there. And again, this seems completely counterintuitive since you look around the world, everything looks, of course, you're seeing reality. What's the problem? Well, let me show you what the problem is. It's referred to as the inverse problem. It's, again, been around for at least 3 centuries, probably longer if I were a better historian of vision research. But I'm going to show you why this problem exists based, again, on just taking one example of luminance, how we see light and dark, and what the problem is. So we're used to thinking about stimuli. I think all of us tend to think this way. Certainly I did until sort of getting involved in this work in recent years. We tend to think of visual stimuli as coming from the world and being passively received by our visual system. So there are objects out there, you guys are sitting in front of me, and light is coming from you, from the illuminance on the ceiling here, etc. And we're used to thinking of the eyes as passive recipients of stuff that's coming from the world. But I think if you think about it, and the point of this slide will be to make you think about it, that's really not such a good idea. What's really happening is that the eye of us or any visual animal is basically being immersed all the time in a sea of electromagnetic radiation. So electromagnetic radiation, is the stuff of photonic energy that's conveyed from the range of gamma rays to the range of radio waves, 20 orders of magnitude or so. And light, what we humans have evolved to see, and I'm going to come back to this point and emphasize that we have specifically evolved to select the stimuli that are important to us, just comes from this little piece in the middle range of this enormous spectrum of photonic energy. So what this means is that out here, with respect to electromagnetic radiation, there are no objects, there are no stimuli. This is just an inchoate sea of radiation over this whole spectrum, and nothing is going to happen until biology comes along and creates a stimulus out of this. Now, the inverse problem is another way of looking at the same dilemma for vision, and this is a diagram that makes that point. And that is that even once biology has evolved a visual system to create stimuli and present them to the retina, there's still a hopeless conflation of all the physical factors that are out there in the world that we need to know about as animals who need to succeed in an environment and flourish over, again, geological time, the evolution of our species. So what do I mean by this? Well, this is all the world. The eye sits here. The world consists of illuminance, mainly in nature from the sun. And that illumination falls on objects in the world of all kinds, and those objects absorb some light, reflect some light in different proportions depending on their atomic structure. And the light that's reflected from object surfaces travels through an atmosphere that again affects the light that reaches the eye. And the point of all this is that the illumination, the reflectance, the transmittance, and a whole bunch of other factors involved in the generation of the light that reaches our eye, they're all conflated. That is, they're all mixed together, retinal stimuli. There's no logical way that you can take this conflated mess and work backwards to understand, to dissect, to disentangle the factors that are conflated in the stimuli. So this, as I said, is called the inverse problem. So the combination of the lack of information in this sea of electromagnetic radiation that's reaching us, and even after we're evolved, the conflation of these stimuli in a way that simply can't be disentangled by any logical algorithmic procedure, is the fundamental problem I would claim that vision has really had to evolve to resolve. And I use the word resolve advisedly because an inverse problem, basically z equals xy, where you know only z and you have no idea what x and y are, you can't solve that problem. You can at best only contend with it. And the question for the rest of this talk, basically, is how has vision evolved to contend with it? So the argument is that visual animals have circumvented this problem. Again, I use the word circumvented advisedly in the sense that there's no solution to it, but vision has obviously gotten around it in some way, or we wouldn't be sitting here having this conversation. And the argument that I'm going to make is that what's happened is that vision has evolved to create stimuli and to restrict stimuli, specifically to those that have produced reproductive success, and that's how the problem is being resolved, circumvented, if you like. So this is, again, a tough pill to swallow. You mean there are no stimuli coming from the environment? There's nothing coming from you that's telling me you're sitting there, hopefully being attentive to what I'm saying and thinking hard about all these things. Yes, that's what I mean to say. There are no stimuli out there. The stimuli are all a product of evolved visual systems, of biology. And let me see if I can make that point here in sort of a diagram. So this is a diagram about the creation and restriction of stimuli by visual systems. So what are the factors that take this mess of electromagnetic radiation and make something out of it by creating stimuli that we can use, and in what way do we use them to get back to the world that we can't, by the arguments that I've just presented to you, know anything about directly? So here are the factors that are involved, and there are lots of them. These are just exemplars, if you like. But they're obviously evolved pre-neural determinants of stimuli, and those include the refraction of the cornea, the accommodation of the lens, the projective geometry that's involved in image formation. All of these factors are not properties of the world, they're properties of biology. They're properties that we bring to the mess that's out there in the sea of electromagnetic radiation that we're confronted with. And once you reach the retina, hold on, let me just finish this and then I'll let Colin interrupt me with some pithy point. When they reach the retina, then you have evolved neural determinants. So those include the topography of receptors that have evolved to form the retina per se. You have the receptor sensitivity that, again, we've evolved specifically to see a range of the electromagnetic spectrum from 400 to approximately 700 nanometers. There are issues such as visual attention. We don't just look anywhere, we look at certain things that are informative. That's another evolved factor. All of that attentional direction of gaze is evolved. It's not a natural thing. So, yes.
Well, just to, I mean, you said there are no stimuli in the world. You're using stimulus in the sense of proximal stimulus, as the psychologists would call it, rather than, I mean, you're not denying the existence of objects in the world. Physical,
of course not.
Right.
No. So there's a real world out there. I mean, nobody would dispute that, and physicists, have instruments that measure the real world out there.
But what you're saying is that the pattern stuff that enters your sense organs can't unequivocally define what kind of object it came from. But there's an asymmetry between the ambiguity of the distal stimulus in defining what's there and the fact that if the same thing is there every time, then the same proximal stimulus generated by it will be there.
Well, I think I'm making a more radical claim that the concept, this is a long-standing concept in psychology, that there is something called a distal stimulus, which is the stuff that stimuli are made of outside of you, and then there's the proximal stimulus, which is the stuff that falls on the retina. And I'm making the more radical claim, that Colin is more or less disputing, that there are no distal stimuli, that that's an ill-posed concept, that what's out there is just this, and because light comes from every possible point in all possible directions from the stuff in the world that is forming reality, that what's reaching the eye is, with respect to objects and the characteristics of those objects, completely meaningless prior to the evolution of a biological visual system that can make sense out of that. That's the argument I'm making. That the concept of distal stimuli out here is not such a hot one. And again, I say I'm being provocative. I don't expect you to swallow this whole hog, but that's the argument I'm making. Okay, so what's the next step in the argument? Well, from what I've just said, there are alternative concepts of stimuli. I'm just repeating myself now, but I want this point to get across because it's kind of critical. One idea is that stimuli arise from the physical properties of the world, and the other is that they arise from the evolved properties of the visual system. I'm favoring this one, obviously, and you might think, well, this is kind of a semantic thing or a philosophical distinction. And that might, in fact, be the case. I mean, the difference between the concept of distal stimuli that Colin has suggested and what I'm saying doesn't really make sense would be, indeed, a kind of a point of marginal interest if it were not for the fact that, as I'm going to try and convince you now, this is how the visual system has resolved the inverse problem. It's this distinction, it's this creation of stimuli by the visual system that allows without any knowledge of the world, our subjective sense of vision, visual perception, to emerge as something that really works in reality. So let me tell you what I mean by this by turning to the fourth of these 6 points, which is that we can predict stimuli, we can predict the consequences of biologically produced stimuli by their frequency of occurrence and explain the phenomenology of, what I showed you in the first few slides of how we don't see lightness and brightness in accord with the physical reality of luminance values. You need to explain that, and now I'm going to turn to the question of how you would explain this in terms of the biological creation of stimuli and their restrictions to ones that have specifically led to reproductive success. So here's, again, one example of many over the last decade or so. We apply this to all the basic qualities of vision. Again, not just lightness and darkness, but the perception of color, perception of form, line length, angle subtents, motion, and a whole bunch of more specific phenomena like the corn-sweet edge that I showed you before. All of these we've sought, and I think with reasonable success, to explain in the same terms. And I'm just showing you an example of one of these, that is how to explain the phenomenology of the same patches in two different surrounds looking differently bright. What's that about? How can you explain this empirically? How can you explain it on the basis of intelligence? So here, this is technically, not technically, but this is how you, this is technical to a point, this is how you go about it. So predicting what we see on this basis, and the question is, why does this patch, which is identical here in these two surrounds, a dark surround and a light surround, again, these two patches, even though this is just a diagram, they are again the same luminance. Why do you see them as different? How can that be explained in terms of the biological generation of stimuli and their restriction and effectively the frequency of occurrence in human experience, not in personal life, although that counts too, but in evolutionary time over the whole history of the species. So what you can do to explore that question is take a dark surround, take a light surround, just two stimulus patterns, and even though I'm using these simple stimulus patterns, I want you to understand that this would work for any pattern of luminance. We don't have to limit it to, all the pixels in the surround being dark or light, but this is certainly the simplest case. So the question, and that's signified by the question marks here, is, in your experience, not you personally, but in the experience of human beings, looking at nature, assuming that nature hasn't changed very much over the eons, what would be the frequency of occurrence of the luminance values that you would get in this surround versus the luminance values that you would get in this surround? So what you do is take a database of natural black and white images like this, and you take these templates and you apply the templates literally millions of times to the images, and you determine in that way the frequency of occurrence of the luminance values in this patch in a dark surround and in a light surround. And what you see is not entirely unexpected, that the probability distribution for the luminance values here and here are going to be different. And what is evident here is that the distribution of luminance values for the central square in this surround is shifted to the left, is darker than the luminance values that you've experienced, human beings have experienced over time in the light surround. Again, this is derived just empirically from sampling literally millions of times a database of natural images. Well, if you want to ask what's the explanation of this phenomenology, you have to put these data, the frequency of occurrence, into a cumulative probability distribution, because you want to know the rank. How often was this central patch or this central patch, how often was it one luminance or another over the course of experience with these images? And to do that, you simply have to transform the probability distribution into a cumulative probability distribution, because each of the probabilities here you can see, if you take the probability of the value here, well, you're going to always get two probabilities, but if you transform this same data into a cumulative probability distribution, then you get a rank of how often, in terms of a percentile value, did this luminance, and now we're picking a specific luminance and putting it in here, how often did this luminance appear in this surround, and how often did the same luminance appear in this surround? And the answer is that you get different ranks. The rank here is much higher than the rank here. And the idea is that the reason that you see this patch and this patch being differently bright, even though they're physically exactly the same, is that this is how the system has evolved to solve the inverse problem. That by taking the frequency of occurrence of experience and having evolved to generate that frequency of occurrence, because you're generating the stimuli, biology is generating the stimuli, not the world, you can relate the subjective experience that you see in terms of lightness to the selecting of stimuli, the frequency of occurrence of stimuli that have allowed you to succeed over evolutionary time. So that's, again, a hard thing to swallow, and we probably need to discuss that, but that's the argument here. And based on that kind of an argument, there's no reason to think of the response to visual stimuli. Again, understanding that they're biologically created, not just something that comes to you passively from the world, that they're no different from any other reflex. So, yes?
Just a question of my understanding. So could you just go back to the last slide, please? So at first, it looked like you were finding out the probability of luminance of the central patch given the surround patch. Right. And that looked like something you do irrespective of what's going on in the eye. You're just looking at various black and white images of the world.
Yes, but understand that these black and white images, these are on your retina. They're not out there in the world. We could go back to that sea of electromagnetic radiation slide that I showed you before. So the idea that all of us have, I mean, it seems so compelling that it's hard to think in any other way. We think of images being out there, but they're not. They're on your retina, biologically created by your visual system, by those pre-neural and neural evolutionary steps that I mentioned.
You're detecting is an objective property that you can work out on the basis of photographs of the world without knowing anything about the nature of the visual system.
Yeah, but you have to understand that an image, when you take a picture of the world and you think, oh, okay, that's a picture of objective reality, that image doesn't exist except insofar that it's on the camera plane, the film plane, which is just a surrogate for your retina. Again, the camera is a simplistic device that's like your eye. It's generating an image that is happening in the same way that the evolved refraction of the cornea, lens, projective geometry, and so on have formed that on your retina.
There's nothing experiential feeding into that model yet.
How can what?
There's nothing experiential feeding into this model yet. We're purely talking about how light through a lens is
that's true.
picked
So
up
that's
by
that's why you have
photographic.
to. So that's why you have to take millions and millions of samples to find out what the cumulative experience has been.
Where does the experience come in?
Cumulative experience.
Where does the experience come in here? Because so far we were just talking about light being detected on a photographic film. We haven't talked about experience yet. So that's why I was asking the question, because when you went to the bottom two graphs here, you started talking about experience, and I wondered where experience came in on this picture.
Okay, let's go back to this one. So the argument here is that you can imagine a camera here or an eyeball. Same difference. That the camera stands for the evolved apparatus of your eyeball. It's not a machine that's detecting something that's out there in the world as an independent reality, other than insofar as it's acting as a surrogate for the evolved properties of your eye. And the idea that there's an image, again, I'm completely sympathetic to your question. I never would have thought of this until quite recently. But the reality is that there are no images out there. The images are something that's created. It can be created by a camera, or it can be created biologically by your eye. The camera is just a surrogate for what your eye is doing.
I take it in my visually. I take it that there's a big difference between the projection of light on the back of my retina and something that's a conscious experience. I mean, those two things aren't the same.
Oh, absolutely.
So that's why I'm asking, what you're saying on that last slide seems to be about projections of light and how they affect either photographic plates or the back of the eye. We haven't yet talked about subjective experience, and you moved very quickly from...
Here we're talking about subjective experience. So this is your subjective experience. These two patches are identical or similar to the ones I showed you before. Two photometrically identical patches stuck in two different surrounds. And the question is, why do we see that subjective experience? Why is our subjective experience different from physical reality? We know these two luminances are the same, but we don't see them as the same. We see this one as darker and this one as lighter, and the question is why, and that's what I've been trying to explain.
And so your answer is that probabilistically you see that combination more, and that's why.
Yeah, but that's kind of getting a little bit off the track. That's true. But it's not because, again, remember that you really need to keep this idea in mind, that it's not like there's stuff out there that you were seeing more of. Keep this picture in the forefront of your mind. This is just all you've got, all the visual system has is a bunch of photons. And those photons are, every point on the cornea is receiving photons from every possible direction, from every object, from the moon, the stars, everything else. This is just, as I said, an inchoate mass of meaningless photonic energy, and until the visual system evolves to deal with that, you've got nothing. The only thing you've got is, and that's why I sort of colored this yellowish, the only characteristic of this sea of photons is that because we live on the planet Earth, and the sun is our star, and the sun has a greater energy per unit time reaching the surface of the Earth from the middle range of this than from cosmic rays or radio waves, that the only bias in this environment is toward the middle of this enormous 20 orders of magnitude range. There are no, and again, I said I was going to provoke you to think about these things. There are no images out here. There are no images until the eye turns this mess into images.
I can pick up on what I think Fiona was saying. I think she's drawing a distinction between exposure and experience. I mean, you're appealing to some kind of probabilistic process during evolution. You tend to see certain conjunctions. You tend to receive certain conjunctions of pattern in your retinal image, and that ultimately then leads to mechanisms for interpreting that image, which we would call experience. But the kind of, what worries me, even if you accept what I said, what worries me there is a circularity, because to have the experiences, you've got already to have a mechanism for detecting to what's on your retina, responding to what's on your retina.
Well, so you're asking sort of a very deep question about the nature of evolution. Where does it start? And, you obviously didn't have an eyeball with a lens and a cornea at the beginning, so this is over 3.4 billion years that these things have happened, and they've happened in a way that didn't begin with an image. It began, God knows where, with a phototropic organism of some kind that had, a limited ability to respond to light, but nonetheless an ability, and things went on from there. That's the idea. So, I was making the point, and these are all, okay.
Is it clarification?
Yeah, just a clarification. So you said that the distinction between the two stimulus would depend on the probability of the activation pattern, right? So,
yeah.
But why does one get brighter? It can be darker, right? Why does the certain thing? Why the high probability has to be?
Because we evolved to see luminance in this way. It's not something that's coming from the world. It's something that's coming from our evolution and restriction of stimuli to that probability distribution. Those probability distributions are coming from images, but the images, remember, don't exist prior to or separate from the ability of the evolved eye to create images. That's the argument. So, as I told you, this is really a hard sell, and you're making me work. That's good. So, fifth point. From this whole vantage, perceptions are no different than any other reflex. So I'll come in a minute to other ways that people these days are thinking about vision that are obviously different from this. But the kind of implication from what I've been telling you is a very simple one, that visual perceptions are just reflexes. So let's look at a sort of a Sherringtonian reflex. This is your standard knee-jerk response. The quadriceps extends when you stimulate the mechanoreceptors in the muscle, the stretch receptors in the muscles, and that information from these stretch receptors runs centrally, interacts with neurons in the spinal cord, comes back and makes the muscles contract, your leg extends, and that's taken as a paradigm of a very simple reflex. And the argument would be that visual perceptions are really no different than this. There's no conceptual difference between them, even though the complexity of the reflex arc may be greater. But the complexity of this reflex arc, and Sherrington, brilliant guy that he was, characterized reflexes as a convenient fiction. He knew that all reflexes, including a simple spinal reflex like this, involve much more than just these few neurons that you see diagrammed in all textbooks. That there was ascending information going to the cortex, descending information going to the cortex that would affect these. And so my point is not that you could take it either way, that a simple reflex is more complicated than it seems, but the point is that conceptually, no difference between the input-output response of a perception again being in the causal chain. I mean, we don't perceive this. This happens, well, we can look at our leg and see that it extends and feel the muscle move, etc. But it's not considered perception. The only difference between the output of vision and the spinal reflex that's shown here is that we're aware, or often aware, of what we are provided by our visual system. So perception is just a feature, and certainly a puzzling feature. Why do we need it? Why do we need to perceive things in the first place? That's a separate sort of philosophical question. But there really is no reason to think that perception, again, being in the causal chain to an eventual behavior of some kind, whether it's the elicitation of a motor reflex, whether it's a motor response or elicitation of a memory, an emotion, a motivation. These are all behavioral consequences of visual stimuli, that they're all just reflexology. So that's, again, something to think about, and you can debate it or not, but that's the claim I'm making. And the final point I wanted to make here is that if you really want to understand, I mean, if you take seriously what I've been telling you and you want to understand why it is, going back to Hubel and Wiesel, and why is that people really don't know how that circuitry is contributing to perception, how the receptive field evidence for what's going on in the primary visual pathway, and I'll show you what a receptive field is in a minute if some of you don't know that already, that, again, there's no way that I can think of that you're going to find out how that stuff is really working, what its purpose is, what it's doing, other than to mimic the evolution of the visual system. Now, that sounds crazy, and I think it would be a crazy thing to imagine as recently maybe as 20, 25 years ago. But nowadays, as you, I'm sure, mostly know, genetic algorithms and computer simulations of artificial neural networks evolving to solve a problem are pretty routine stuff. And the question is, if you do that for vision, would you find out what the mechanisms that Hubel and Wiesel and many, many others describe as underlying the response to a visual stimulus? Would you find out something about what that machinery is really doing, and would it accord with what I've been telling you? So this is just to remind those of you who don't know or have forgotten what a visual receptive field is. And so this is a diagram of the sort of work Hubel and Wiesel did in the late 1950s and 60s. And they would take an anesthetized cat, record from a single neuron in the cat's visual cortex, present the animal with stimuli on the tangent screen in front of it. Even though the animal is anesthetized, its visual system is still working, or at least working to the extent that this kind of result is observed. And what they, and since then many, many others have found, is that, of course, there is for any given neuron that you're recording from here, there's a place in the visual field of the animal that causes the cell to fire, and that's the locus of the receptive field, and one can define in terms of its visual angle how big the receptive field is. So you put the stimulus down here, nothing happens. Up here, nothing happens. But if you have the stimulus in a circumscribed region of the visual field, the cell will fire. And the thing that justly made them famous was the discovery in the early 1960s that the receptive fields were selective. That is, it wasn't just the location of the receptive field, or the stimulus rather, in the visual field. The cells were also responsive to specific characteristics of the stimulus. In this case, the orientation. So this is a diagrammatic view of the action potentials elicited by this stimulus at different possible orientations going around the clock phase. And again, just an example, but this was characteristic, that there'd be some orientation that would cause maximal firing of the cell being recorded from, and as you deviated from that orientation, the firing became less and nil at some point. And what they deduced from this, and the list of receptive field properties has expanded enormously over the last 50 years, is that visual receptive fields were selective. So they have a bunch of properties that they describe and that many others have amplified since. So this is just, and again, I'm not going to go into the details here because there's neither time nor really reason to do so. But this is an artificial neural network that is simulating the retina here with sensor neurons that are synaptically connected to integrating neurons that are producing an output of responses that can then be, I don't like to use the word learning because I don't think evolution is, well, it's a form of learning, of course, but it's not like learning, your ABCs. You can use this kind of paradigm to ask, if you take the framework that I've been arguing for and evolve artificial neural networks on that basis, that is, you evolve them to respond to the frequency of occurrence of stimuli that are being generated by images that would have been the natural stuff for us, the naturally restricted images that we human beings have seen over the eons. What would the receptive fields look like? Would they look like the receptive fields that you see in biology, that Hewell and Wiesel and many others describe? And again, without going into details, so this is receptive field properties after evolution using the percentile rank, I showed you in the slide before, of stimulus occurrence as the measure of reproductive success. If this is what the visual system has been evolving to do, if this is the way it's been evolving to resolve the inverse problem, then you would expect that the receptive field properties of the neurons would be similar to those you see in recordings from cats, monkeys, many other species. And I'll skip the details of this. Suffice it to say that this is illustrating, for those of you who know about receptive field properties, the classic center surround of an on-center, off-center cell that was evolved by the artificial neural network on the basis that I just described to you. And this is simply a depiction of the receptive field properties. And they do indeed show the same characteristics that you see in biology. And those consist of, first and foremost, an on-center, off-center relationship, or conversely, an off-center, on-surround relationship. So you can evolve either type of a neural network, such as the one I showed you. They evolve luminance gain control, which is the equivalent of saying light adaptation, and they evolve contrast gain control. These are the three basic characteristics of biological receptive fields, and all of these emerge in artificial neural networks that are evolved by simulating, by using the same kind of image data. They evolve the same basic characteristics as biological neurons. So let me just comment, this is the last slide before the summary, just again to get you thinking a little bit about different ways today that people are thinking about vision. Well, I've told you in the last, well, I guess it's more than 45 minutes now with all the interesting interrogatories. These are some of the ways today that people are thinking and conceiving vision. And I needn't tell you that what I've told you in this hour is definitely a minority view. I hope the minority is not one, but it's certainly not something that most people accept. So what are the various ways that people today are thinking about how vision works? Well, the first of these is what I would call the sort of old-fashioned way. The implication of the work that began in the 50s and 60s was that, and still is for many people, that the visual system creates images, and from those images you extract features. And those features are processed by the machinery of the visual system, and they're represented someplace in the brain, and that the representation of the physical characteristics of the images is what you end up seeing. So that we can really rule out, I think, with certainty, just based on those first few phenomenological slides that I showed you. We're obviously not seeing lightness and brightness, lightness and darkness in accord with the physical reality of the world. So I think an awful lot of people are still kind of mired down in this way of thinking about it, but that's just not going to do the job. So that has led to two different ways of thinking about vision that are basically founded on an idea that Helmholtz put forward in the 19th century, and what he said was that visual perception, is unconscious inferences, that you gather data, and he thought about this, and others who are working with this are thinking about this not in terms of evolutionary time, but individual time, that you gather data and you make an inference, an unconscious inference, because you don't have to think about it, but that your perception is an inference based on the data that you have experienced. And that can be put in terms of Bayes' theorem, and we can talk about that if you like. That's one sort of camp that is explaining vision in terms of the power of Bayesian decision theory. And another camp is making the similar supposition that vision is inferential and gathering data, and the perception follows from that. But they're arguing that this is based on efficient coding. And this is comes really from information theory that began with Shannon's paper in 1948 and has gone on from there. Horace Barlow and other people very quickly in the 1950s applied information theoretic principles to vision and argued that it was inferential, but the inferences were coming from the efficient coding of information. But that would be, just as it is in telecommunications, essential for any system that was transducing and transmitting information to a distant site, as action potentials and synaptic potentials do. And this is what I've been telling you about this afternoon. So I think we can cross this one out. The jury is still out on whether what I'm telling you makes any sense, and whether the arguments are ones that people will eventually accept, or whether these perhaps are better ways of thinking about vision. I don't know. I've colored this one green because obviously I'm in favor of it, but that doesn't help much. So let me just sum up what I've told you, because I think this is what I started with, but these are the key points that you need to think about. Number one, what we see is not the physical world. That's for sure. No debate. I don't think anybody, and people may not like to think about that. They might want to sort of trivialize these as illusions, blah, blah, blah. But point number one is just a fact. I think point number two is also a fact, that whatever you think about the argument that I made, that the challenge, the major challenge for vision is, without much dispute, that the conflation of all the parameters, the physical parameters that are out there in the world in retinal images, really make it impossible to think that vision could proceed in any way, shape, or form by an analysis of features on the retina. That would lead to a disaster, and it's not hard to show that if you were to see luminance, for example, as luminance, you'd be dead very quickly. I mean, you'd be making horrendous mistakes in the environment, because just the fact that luminance doesn't really represent the physical world, it represents the information that gets onto your retina, but not the physics that you need to respond to. The third point has to do now with a more controversial point, that the circumvention of this quandary, the inverse problem, is to create stimuli so that they are biogenic, not generated by physics. They're simply not, for the reasons, at least in my opinion, not for the reasons that I argue. And that as a result, the frequency of occurrence of stimuli, their percentile rank in cumulative human experience, predicts what we see. And that's evidence that it's not a bad idea, because all of those phenomena that are otherwise really very difficult to explain can be rationalized in this way. And this maybe is not a terribly important point, but I think it's worth thinking about, because one tends to divide things into top-down, bottom-up, and a whole lot of, well, I shouldn't say it, but I mean, nonsense, in my view, that is just not justified, that there really is no reason for thinking of visual perception as being any different fundamentally than any other reflex, including the simplest spinal reflex. And finally, and this very much remains to be seen because very little work has been done on it, that if you really want to understand what the visual system is doing, what the mechanics are really accomplishing, how they're doing this task, and I think the best way to do this is by evolving neural networks, which is today a real possibility. So these are the column will recognize this. This is Clark Key Station right here, and these are the characters who are presently in the lab, and these are previous collaborators, and I especially highlight Bolato and Catherine Howe as having contributed enormously to this work as postdocs in the lab. Previously, there's the website if you want to test any of these things and see that this is all legitimate and not hocus pocus. Just type in my name, Purves Lab, and you can play to your heart's content with all these things. And the last thought I'll leave you with is this, that really, when all is said and done, it may be that the visual system and what it's doing is not as much different from what the liver is doing as a lot of vision scientists would have you believe. So let me take more questions and end there.